Hi, my name is Michael Wong. Welcome to everyone to this IWOCL SYCLcon 2021 and everyone viewing this in the future through the internet land. I'm the chair of the SYCL working group in Kronos, and today I'd like to talk about three things. SYCL's insanely enormous growth in momentum from 2016 to today, a fundamental shift towards specialization and extreme heterogeneity, and that SYCL can be easily built for those specialized devices. It can be easy to use due to the C++ productivity, and it's easy to convert from CUDA while maintaining comparable performance. One thing that I have learned from decades of experience in working with parallel programming models is that there must be longevity in those that are chosen. There can be a 20-year lifetime across a range of supercomputers that need to have a common and standard way to write software. Hardware changes frequently and much faster these days. Look at this diagram that shows how the US National Labs, funded mostly by the Department of Energy, have quite a range of different processor architectures. What they're recognizing is that they need a programming model that is stable and can support the latest supercomputers, and it needs to be an open standard there that they're able to influence to ensure it brings the best for developers across not just their laboratories, but for everyday people who need to use computers. These machines cost hundreds of millions of dollars commonly, and their usage spans across laboratories and departments, not only in the USA, but also in Europe and other parts of the world. Now, I was the OpenMP CEO for a long time, and the first version of this specification was in the early 2000s and has lasted 20 years. I envision the same for SYCL because it provides the right elements for everyone to develop highly parallel, accelerated, portable software. The latest version of SYCL 2020, which launched in February of 2021, to bring a new level of expressiveness and simplicity for developers who wish to program heterogeneous parallel processors using modern C++. The result of 3 years of work, SYCL 2020 aligns closely with ISO C++17 to simplify porting of standard C++ applications. While maintaining backwards compatible with previous SYCL versions, SYCL 2020 provides significant new functionality for improved programmability, smaller code size, and faster performance, and is subsequently now being widely adopted in desktop and supercomputer markets, as well as embedded systems. On SYCL.tech, you can see a cumulative listing of SYCL projects, which have been growing steadily since 2012 and accelerated in the 6 years covering all areas, including benchmarks, frameworks, libraries, and scientific applications. SYCL momentum has been huge on all fronts in the last 6 years, but especially in the last 2. This is a chart of the many open source public GitHub projects showing the growth of Intel's Clang LLVM port in red, Hipsicle in blue, Tricycle in yellow, Celerity in pink, and SYCL GTX from Peter Zuzek, who works now at CodePlay, in green. So the branch is mostly dormant. There's also now Paul Kier's Motorcycle, I love the name, in brown. Inteon's Polygeist SYCL in orange. The other graph shows the growth in the number of Stack Overflow questions on SYCL and one API from when I started in 2016 when there were 14 to over 600 questions this year after 6 years. A 600 times growth. The number of people attending the working group has doubled too, thanks to contribution from an insanely talented group of dedicated people across many companies, some of which you will hear in this conference, talking about SYCL features, SYCL projects, and SYCL research. I'm so grateful for all the help this group has done to build this SYCL momentum, and they are also the nicest bunch I have worked with in my several decades career in working on many different consortium and standard organizations. Looking at GitHub, for any mention of #include CL SYCL.hpp back in January, I found 17,500 mentions, and recently in April, I found 21,000. Looking for SYCL/SYCL.hpp back in January, I found something like 8.2K, and now I have 8.8K. totaling almost 30,000 K in total source files. The market needs SYCL, as can be seen by the various elements of growth, from 2016 IWOCL in Vienna when I first attended, to today's virtual SYCLcon. The growth has been amazing, and the reason is because it's easy to build SYCL on any device. From 21 to 247 projects, from 2 to more than 12 implementations, from 2 to 10 plus platforms, double the working group numbers, over 600 GitHub stars, and Stack Overflow questions. We now have a safety critical exploratory group, one book and many articles, and over 30,000 GitHub include codes. From no supercomputing presence, no automotive, no Clang or LLVM branch, no common one-stop website, no common teaching material, and no HPC presence. We now have had supercomputing Bob 5 years in a row, use of SYCL in automotive Renesas R-Car, an active DP C++ Clang branch by Intel, but now collaborated by many people. One-stop website, SYCL.tech, one-stop SYCL teaching material in SYCL.academy, and support on 7 HPC systems. SYCL has entered mainstream because it is an open standard with open source implementations, with open cross-company collaboration. We're preparing to enter a new phase of co-design with all forms of extreme heterogeneity. A SYCL survey is coming to ask what language functionality would you like to see more broadly supported, such as C++ 2023 core support, USM, unnamed kernel lambdas, or hierarchical parallelism. So that we don't rest on our laurels and success, the market also needs SYCL to evolve. So this is a call to action of the things I see SYCL needs more of to succeed. These include getting more and bigger workloads using SYCL, some of which is already happening. We will make more and more ISO C++ compile together with SYCL easily. Our official project this year is to complete conformance, improve user experience with a better out-of-the-box experience in the SDK, and get us on an online compiler like Compiler Explorer. There are several other things like having a SYCL graph, safety critical tooling, and I will talk more about data movement still being king and how important CUDA SYCL conversion is. But first I want to show you from the programming research forum from NASA, showing how SYCL is starting to penetrate NASA where it has been traditionally been mostly Fortran and Python. The market needs SYCL to succeed, to offer democratization. That means everybody gets to influence it. And we're pushing forward with exciting new features. You can check them out on public GitHubs, including things like scope parallelism, multi-device queue, command group properties, buffer USM interop, pipes, accessor restrict property, accessor property, NQ barrier, bfloat 16, and general properties. In my career, I have seen many parallel acceleration languages come and go. That graveyard is littered with these experimental languages or even mildly successful languages that fail to reach mainstream. One of the things we were trying to learn in this programming research forum at DOE is what makes languages fail. The other thing we were also trying to prepare for was the post-exascale era, or zetascale, when we will reach from 10 to the 18 flops to 10 to the 21 flops. But besides all the great talks, the most interesting aspects were the breakout groups. And of all the breakout group topics, these topics were considered the most important for future programming model. And it is instructive on what was chosen by a group of 100 researchers, scientists, and industry leaders. These were performance portability, domains in need of a DSL, language level parallelism, performance debugging and correctness, task-based programming, distributed memory, AI ML in programming systems, sparsity or irregularity, validation, verification, safety assurance. From the ASCAR workshop in 2021, Niels Thomson's excellent keynote, In there, he said silicon-based transistors are nearing the limits of miniaturization, and the slowing pace of performance gains from smaller transistors is driving large-scale disruption of the entire computing ecosystem. As a result, the high-performance computing ecosystem has transitioned from being dominated by a few relatively similar general-purpose central processing units, architectures, to being dominated by a few relatively similar, increasingly general-purpose graphics processing unit, accelerator architectures. In alignment with the computing industry, it seems likely that the CPU-GPU architectures will rapidly be augmented by a diverse set of systems that comprise a broad portfolio of commodity plus customized modular components that include CPUs, GPUs, and artificial intelligence accelerators. 2, where specialization provides benefits, this new ecosystem offers opportunities to significantly improve the performance, energy efficiency, productivity, reliability, and security of applications. But exploiting these opportunities requires the development of innovative techniques and tools to rapidly co-design future software and hardware using verified, data-driven methodologies. In other words, the end of Moore's law and Dennard scaling means we need more specialized devices, and that has only become economical, whereas it wasn't before. So specialization is more attractive now that CPUs are improving slowly, but volume is needed to be worth designing a specialized chip these days. In the direction of more specialized devices, we're heading towards extreme heterogeneity. These days, it's not just about GPUs, but also ASICs, FPGA. But how do we measure these different kinds of accelerators? In an article by KD Nuggets, today people are moving from flops to tops, or tera operations per second. It's a measure of the maximum achievable throughput. Now, the definition of TOPS is a moving target, largely driven by ML today. Is TOPS the new flops? It seems not, because even TOPS is not telling all the truth, but it is pointing the direction towards more diverse forms of heterogeneity. One of the definitions of TOPS is the silicon energy efficiency of a multiply accumulate unit, and it improves quadratically with reduced bit width. This graph shows the performance of an NVIDIA GPU, a Groq ASIC, and an FPGA. The number of TOPS the silicon can run. Now, GPU is the obvious reference. Based on NVIDIA's numbers, it does not have the best performance, but it does an honest job of putting the 130 TOPS into action. As a lot of the silicon goes to the gaming ability of the chip, the GPU seems to have limitations in processing this simple neural network. There's a lot of hype building around ASICs for machine learning, and it is certainly driving hundreds of millions of dollars into that field. One startup seems to be ahead of the others because it announced an impressive 1,000 TOPS with expected performance about 4 times higher than the GPUs for ResNet 50. As the ASIC is designed for this kind of neural network, it is not surprising that it demonstrates higher performance than a chip that was not intended chiefly for machine learning. However, what is surprising is that about 7.5 times the number of TOPS results in only about 4 times the performance. In other words, relatively to TOPS, about 50% of the chip is dark for neural network computations. This is quite a lot of silicon unused but paid for, especially for a chip tailored for neural network computations. Now, FPGAs have long been considered a possible solutions for neural network inference. However, the programming challenges have impeded adoption. Now, some companies, including some of the SYCL working group members, are now working on software solutions that eliminate the need to program FPGAs for machine learning. These solutions make the FPGA look like a GPU to AI frameworks and enable computation of neural network without FPGA competence. This works quite well in terms of silicon efficiency. While the FPGA supports less than 1/6 the TOPS of the GPU, it delivers a similar number of images per second. Relatively, the silicon of the GPU is only about 15% used, and the silicon of the ASIC only 8%. Therefore, even though you are giving up some TOPS, you're getting much greater efficiency and comparable performance with an FPGA. There's even more from the Programming Research Forum recently. From Professor Torsten Hoffler's excellent talk, and is related to the second element of TOPS, and that is in TOPS, the data movement, the silicon energy cost improves linearly with reduced bit width. So as the number of parameters in deep learning reaches billions now, it increases the cost to train to almost $12 million. There are 2 published articles on why data movement is all you need, and it is still king, and how it is going to get worse with deep learning inference, especially in sparse matrix. So back to the ASCAR form, where they show that co-development of hardware and algorithms creates transformative new opportunities by cooperatively designing algorithms and hardware together. The rapid disruption and change of the hardware and computing ecosystem amidst new opportunities for co-design. These opportunities combine new hardware and algorithms and can present transformative opportunities. In an era where specializing hardware to the application is the only means of performance improvement, the economic model for the design of future systems is going to need to change dramatically to lower design and verification costs for the development of new hardware. Open source is not just in software, but hardware. The ASCAR report shows that specialization is the most promising hardware technique for continuing to provide year-on-year performance increases required by all users. But specialization needs to have a well-defined application target to specialize for and may not be applicable to all domains. Post-SYCL HPC systems will become increasingly heterogeneous environments with heterogeneous processors, accelerators, whether they are commercial designs or emerging reconfigurable hardware or bespoke architectures that are customized for specific applications, optimize hardware and software for particular tasks or algorithms, and enable performance and or energy efficiency gains that would not be realized using general purpose approaches. These days, there are chiplets or super chips. There are licensable IP for server class processors like the ARM-based specifications. There are open source hardware and open silicon compilers like from RISC-V. There's photonic resource disaggregation. There are standardized accelerator interfaces such as those introduced by Intel's Level 0. There's advanced hardware description languages and hardware generators. There are new accelerators and FPGAs and CGRAs. There are advanced packaging technologies for heterogeneous integration. There's open source and extensible compiler frameworks like MLIR and LLVM. There are AI integrated applications, and there are new programmable abstractions and frameworks and languages like SYCL, COCOS, and Raja. This slide is about parallel industry initiatives and the possible future roadmap of SYCL, where we release SYCL 2020 based on C++17. This means it enables exciting C++ features such as CTAD and deduction guides that makes code less verbose. There are also a number of other great features. You will also see that we're projecting tentatively that a future SYCL will be released after 2021 and will likely be based on C++20, which was released this year. We expect the next version, therefore, to support all of C++20's goodness like ranges, coroutines, and modules. Here are the 3 main industrial commercial implementations of SYCL from Intel, CodePlay, and HipSYCL. And just like a great Major League Baseball team, we also have a great farm team of experimental branches showing how easy it is to build a SYCL implementation for some unique custom processors. Some of these by students like SYCLcon, scientists like Celerity, educators like Paul Kure's Motorcycle, and of course AMD Xilinx support for FPGA in Tricycle. So one of the questions many of you guys have asked, and indeed Jacob Kahn from Facebook's Flashlight project have asked, is for a given device kind, what is the SYCL compiler that you would try first? So here's some migration advice. If you're on NVIDIA GPU, then consider DPC++ that's supported today by CodePlay. It is open source and is optimized. If you're on an AMD GPU, sure, there's the DPC++ experimental support today by CodePlay that's open source, but even better is SYCL. That's open source today and is supporting the European Processor Initiative in Da Vinci, Lumi, and Carolina. If you're on Intel GPUs, then definitely use the DPC++ supported by Intel. If you're on some new hardware, Coplay and a lot of companies do support a range of new hardware. Ours is called Compute Aorta and Compute CPP, including RISC-V platform hardware and GPU IP from Imagination Technologies and ARM, as well as Renesas Arcoff Automotive. Also, you can do it on your own, as many students and scientists have. If you're on an FPGA, we've got you covered. There's DPC++ compiler for Intel FPGAs. There's AMD's Xilinx has the SYCL prototypes for FPGAs and CGRAs. If you're on an AI, ML, or neural network chip, then all the major implementations companies can customize support, or you can build it yourself. If you're on RISC-V, Coplay has developed the Acorn stack for RISC-V as an accelerator over x86 CPU. And many people have asked, what about just CPU? Well, all the major SYCL implementations will work very well with CPUs. This highlights the already large and growing SYCL ecosystem, starting with implementations on the left, including the new NeoSYCL and Huawei. Now, there are many research papers. Of this, I've talked about exascale computing projects and Celerity for SYCL cluster last year. Now, these projects allow SYCL to run on exascale and petascale supercomputers as well as distributed systems. PyTorch has minimal framework overhead, and they integrate acceleration libraries like Intel MKL and NVIDIA to maximize speed. Open up at the end of March is the work-in-progress Intel One API backend for Blender's Cycles renderer. This Intel GPU backend focuses on supporting the company's forthcoming Intel Arc graphics cards, is targeting the open source One API based toolkit and making use of SYCL. There still is more code work needed, but it's good to see this coming together to complement Blender's NVIDIA CUDA and AMD HIP support. A walkthrough of converting a code from parallel C++ ray tracing code to CUDA and the work needed to make the CUDA code run on CPU using parallel for each and then convert it to code to SYCL 2020 is available on the SYCL.tech website. Flashlight is a new open source machine learning library written entirely in C++ that was built by Facebook AI Research to power groundbreaking research to enable teams to rapidly and easily modify deep and MLNet frameworks to better fit their needs. There's native support in C++ with One API MKL and simple extensibility makes Flashlight a powerful research framework that's hackable to its core and enables fast iterations on new experimental setups and algorithms without sacrificing performance in a single repository. GROMACS is a molecular dynamics package mainly designed for simulations of proteins, lipids, and nucleic acids from Stockholm University. There's also a spec CPU benchmark and is now being accelerated for SYCL. The ATLAS experiment Athena is a high-energy physics experiment looking for Higgs bosons and quarks from CERN and demonstrator tracking chain for accelerators. You can watch the half-day hands-on workshop that walks through the fundamentals of SYCL programming using practical examples and exercises to help reinforce the learning. Attendees will also learn how to compile their SYCL code using the DPC++ compiler to target NVIDIA GPUs, including those on the Perlmutter supercomputer. Lastly, we'll talk about some of the things you need to know to achieve good performance, including best practices for memory management with free time for questions and discussions. We also have a One API SYCL book published by James Rinder, as well as members of the Intel team. Vincent is a physicist turned computational scientist and is working in conjunction with researchers at CERN who run experiments with the Large Hadron Collider. As a physicist, he is of course very interested in the result from these experiments. His work focused on the ATLAS detector, one of the general purpose experiments stationed along the LHC ring that is designed for particle physics research, and it is hoped that it's going to make physics discoveries beyond the standard model like supersymmetry, graviton, or dark matter. The LHC has been built to facilitate experiments and research for at least a decade to come. So software written to run and simulate research must be maintained for more than 10 years. On the far right, you'll see that there's distributed and heterogeneous programming in C++, a workshop that I started in 2016 called now it's called DHPC C++22, as well as the portable heterogeneous programming with SYCL PHPS 22 workshop that is also coming. Codeplay has been involved in defining the SYCL standards since the beginning, and we spent many years implementing our own compiler on Compute CPP, which has been focused on delivering SYCL support to customers. We're also closely involved in working on the One API initiative and have been implementing support for multiple processor architectures for DPC++ and some One API libraries. Currently, we're adding support for all the features of SYCL on the Perlmutter pre-exascale supercomputer and continue to extend this to things like tensor cores. We're also working to extend support in DPC++ for the Frontier exascale supercomputer being built for Oak Ridge National Lab. This work is in a development state, but we expect this to be ready for developers to use very soon. You can find instructions to set up DPC++ for CUDA support on this web URL, and AMD information will be coming soon. The compilation step can't be simpler. Change the target flag to tell the compiler to make binaries for the NVIDIA CUDA target as shown in the command line on this slide. So CUDA is one of the 4 backends currently supported by Intel's DPC++. I'm distinguishing between DPC++ and SYCL here because there are other SYCL compilers, and those compilers vary in terms of which backends they support. Currently, DPC++ implements 4 different backends that are shown in the graphic. OpenCL and Level 0 output SPIR-V instructions that can be ingested by Intel hardware, and the CUDA backend outputs PTX instructions that can be understood by NVIDIA GPUs. Developers can select the backend depending on what devices are available on your machine. SYCL offers some flexibility to enable developers to switch between these backends. So what does that mean for CUDA to be a backend to SYCL? Well, that means that if you're writing a program which uses SYCL, or porting an existing CUDA code to SYCL, and then you compile that code for a CUDA target, then under the hood, SYCL is using the CUDA runtime API to actually talk to the accelerator. Now, there is recent performance results comparing SYCL and CUDA. Here we have cuDNN from it, where NVIDIA has been working on it for decades to improve VGG in ResNet 60 for years. Now, we can beat it in SYCL using the open source SYCLDNN just by using a different algorithm, because we can change algorithm easily using a tiny team in a short time. This adaptation feature, SYCL or C++, is what enables powerful performance portability, because it's easy to adopt algorithms for the workload or for the hardware. I'd like to talk about how One API and SYCL are working together to bring developers an open standard environment for developers. One API provides developers with a platform to build accelerated software, and SYCL sits at the heart of One API, providing a mature open standard interface for developers. When you write code using the One API platform, you will be using the SYCL interface to interact with the low-level hardware on your machine, whether that is targeting Intel GPUs, NVIDIA GPUs, or AMD GPUs. The DPC++ compiler is an implementation of the SYCL standard and makes targeting massive parallel hardware architectures simple and provides you with portability across different targets. The SYCL standard is defined by the whole industry, with myself as the chair. Members from many major processor vendors, national labs, and research groups ensure that the standard continues to meet the needs of companies making processors and the software developers who want to easily target those processors. The strategy of the national labs in the United States is focused on enabling developers with a standard programming environment so that the software they write can be deployed across multiple supercomputers that bring pre-exascale to exascale computing to researchers. Now, we've built a partnership with Lawrence Berkeley National Lab, Argonne National Lab, and Oak Ridge National Lab to enable SYCL on their next generation of supercomputers using the DPC++ open source compiler project. You can see a small snapshot of some of the frameworks and software that is enabled by using the SYCL open standard, from LAMP-PS, a particle simulator, to Eigen, a linear algebra library used by the TensorFlow framework for tensor operations. LEGEN is part of the Legate project, which goal is to create and validate an industrial application for drug discovery in high-performance computing systems. Now, in this context, the evolution of HPC architectures is heading towards specialization and extreme heterogeneity, including future exascale architectures. Because of this, Legate makes of code portability one of its primary objectives. In this field, SYCL matches these goals perfectly, enabling to write platform-independent code while keeping native comparable performance. This is an extremely relevant topic for these days. In June 2019, the Euro-HPC Joint Undertaking Governing Board selected 8 sites for supercomputing centers located in 8 different EU member states to host the new high-performance computing machines. The hosting sites will be located in these countries: Lumi in Kajaani, Finland; Leonardo in Bologna, Italy; Meluxina in Bisen in Luxembourg; Vega in Maribor, Slovenia; Carolina in Ostrava, Czech Republic; Discover in Sofia, Bulgaria; Deucalion in Minho, Portugal; and Mare Nostrum in Barcelona, Spain. Now, 3 of the 8 sites will host precursors to exascale machines capable of executing more than 150 petaflops. Now, that will be in the global top 5 supercomputers and 5 petascale machines. SYCL through HIPSYCL is now in Leonardo in Italy, Lumi in Finland, and Carolina in Czech Republic. And 2 of these, Lumi and Leonardo, are Europe's first pre-exascale machines. CUDA is very widely used in AI and HPC. NVIDIA has done an amazing job with it. There's a huge quantity of code written in CUDA and being ported to SYCL. The US Exascale Computing Program is porting 10 million lines of code to industry standards, including SYCL. CUDA and SYCL are similar enough that in many cases, an automated tool can convert from CUDA to SYCL. Once ported to SYCL, code is still expected to be tuned to each different processor code. Now here, we see Intel is providing a CUDA to SYCL migration tool called Project Cyclomatic that enables developers to have a productive path to create single source portable code for hardware targets regardless of vendors. Now, the Intel Cyclomatic tool is newly open source, and the way it works is that it collects compilation options of the developer's CUDA source file from project build scripts. It assists developers migrating code written in CUDA to SYCL by generating SYCL code wherever possible. Typically, 90 to 95% of CUDA code automatically migrates to SYCL code. And there are going to be inline comments that's going to be provided to help developers complete and tune the code. One example of this cyclomatic conversion is by Zeus Institute Berlin, where they ported the tsunami simulation EasyWave application from CUDA to SYCL efficiently. Its results achieve strong performance across Intel CPU, GPU, and FPGA architectures, and within 5% of CUDA performance on NVIDIA P100. Another conversion example we just built is this N-body experiment that simulates gravitational interaction in a fictional galaxy. There's a GitHub where you can retrieve the code and try it out yourself. Now, because CUDA and SYCL are very similar, it's very easy to port CUDA to SYCL. Kernels are executed in parallel, once per item of data, called data parallel. The programmer doesn't write a loop over the data. The scheduler runs the kernel in parallel across all the data. The CPU host runs in parallel with the accelerator and DMA. Everything is designed to run in parallel, and the scheduler maps data flow and execution to the hardware. Here we see the performance of CUDA and DPC++ all running on the same NVIDIA hardware. The converted code using the cyclomatic tool is actually running even slightly faster. You can see that the number fluctuates at about 8.78, 8.8 millisecond compared to CUDA on the device at 10.19 milliseconds. We actually don't know why, but it's really good to see that the performance is comparable. Now, we're not saying that in every case you're going to get this excellent result. In most cases, we believe it's going to be comparable, and the complexity will vary with the complexity of the code. From a recent machine learning Chronos Summit, we determined people need a higher level safety critical API, as is evidenced by an AUTOSAR Chronos liaison that I'm going to show later on. There's also many industry and standards requiring increasing software safety compliance, even to ML safety. This is because software complexity has been increasing and moving from C to C++ with multi-core and accelerators. Autonomy industries like automotive, avionics, medicine requires AI and ML frameworks that are built on safety critical APIs. So here I'm asking that you join the SYCL Safety Critical Exploratory Group open to non-Chronos members to discuss your use case for safety critical higher level abstraction use cases. So the way we envision it works is that neural network models are trained in the cloud using a variety of frameworks. After training, they're exported and converted to NNEF or Neural Network Exchange format before being passed to a safety critical API for inference. Now, at that point, Vulkan's safety critical does exist, but it provides a safety critical execution layer for computing graphics. You could have OpenVX safety critical profile, which provides safety critical in the specific case of computer vision and neural network APIs. Vulkan, however, is aimed at the lower level, and OpenVX specializes in vision, AI, and ML applications. Now, both are not sufficient to cover all use cases. SYCL Safety Critical bridges the gap between low-level APIs required to build deterministic AI and ML frameworks and high-level programming languages like C++. So SYCL is critical to HPC and AI ML in non-safety critical environments, where SYCL SE is critical to HPC, AI, and ML in safety critical environments. There's also the possibility that you can use OpenCL SE, although that group is still growing, to build depending on which level you want. So recent announcements has shown that Chronos and AUTOSAR has formed a liaison. These are two major groups. One group has excelled at acceleration frameworks. The other group has focused on safety critical using C++ on automotive. And we have already started meeting at weekly Chronos AUTOSAR meetings where we discuss general topics about Chronos frameworks. AUTOSAR has also asked for Chronos members to join specific groups like WG Safe, WG AP Emo, Adaptive AUTOSAR, maybe WGMT, Cloud, Architectures, Update Configuration Management. We're also tasked with updating the design guidelines for using parallel processing technologies on adaptive platforms, using some of our experts, and possibly build demonstrators for OpenCL, SYCL, OpenVX, NNEF, and Vulkan. And this is because SYCL has already been demonstrated to work in automotive AI using the Renesas R-Car consortium, where CodePlay provides a full open standard software stack for SYCL OpenCL SPIR-V for the R-Car AI system on chip. This enables easy transition from NVIDIA GPU platform to R-Car platforms. So to summarize, programming models must persist. We have SYCL 2020 that was launched in February 2021. The SYCL user and developer growth has been phenomenal. The market needs SYCL because it's easy to build SYCL on any device. SYCL is now mainstream. The market will need SYCL to evolve, and SYCL can serve even more extreme heterogeneity. We see that data movement is still king. We need code design with extreme heterogeneity, and in future SYCL, we are moving into emerging transformative technologies. SYCL can be a part of a standard programming model for all HPC, embedded AI, ML, and automotive. SYCL is an open standard with multiple company contributions, with lots of European and Asian projects. So how do you join SYCL? I'm glad you asked. Membership is open to all, and 3 of these don't need any money, including working on the public GitHub, public contribution to specs, and being part of the advisory panel. The AP panel is chaired by Tom Deakins of University of Bristol. Only the working group is needed if you want to know the secret sauce. We now also have an FAQ, which is going to keep up to date. There is a SYCL survey coming, and thank you very much for your attention.